Hi everyone, in this video I will be drawing the acceleration diagram for question 2 of your problem set. Before you start this, I'm hoping you have done the velocity diagram for this question and then calculated your radial accelerations for all of the links that you need. To do this, you measure the length of the line in centimetres, remove the scale, getting a value for acceleration in meters per second. You can then use your v squared on r equation to find the radial acceleration in meters per second squared. Then after that, we can apply the scale that's given in the question to have a value in centimeters that we can draw in the diagram. So let's begin. In the mechanism for this machine, we have the crank OA rotating at a uniform speed of 100 radians per second in the clockwise direction. So same as our velocity question, we have point A rotating about fixed point O. So let's find the acceleration diagram. To start, I'm going to use point A because I know that that rotates at a uniform speed. So the total acceleration of AO equals the radial acceleration of AO plus the tangential acceleration of AO. Now we know the radial acceleration because that was given in the question, 100 radians per second, which we can use to calculate your velocity and from that your acceleration. As the question says it's rotating at a uniform speed, that means our angular acceleration, so alpha, is 0. Tangential acceleration is calculated by multiplying alpha by your radial length. So if alpha equals 0, then my tangential component goes to 0 and my total acceleration equals the radial component of A relative to O. So I can find point A straight away. In my diagram here, A relative to O is going in the clockwise direction. Radial acceleration points towards the center of rotation, so it's pointing upwards towards that fixed point. Put your ruler along the link, set square along the ruler, and then your second set square to get that parallel line. I'm now measuring that length, which is 10 centimeters, calculated using the scale. So this is point A, acceleration of AO, which equals the radial acceleration of AO. That's my first point. Now we move on to the second point in the diagram. You can see that point A is connected to point B and point C as they're all on the same link. We're going to find point C first because point C is connected to another fixed point, O3. If you choose point B to find, you'll have to draw about 6 lines to find point B. However, to find point C, because it has that fixed point, we only need to draw 4. So we're choosing the next easiest point to help us construct our diagram. If we're looking for a new point, then we need a relative equation. So acceleration of C equals acceleration of A plus acceleration of C relative to A. So this C is with respect to a fixed point, and the total acceleration has 2 components. We have radial and we have tangential, C relative to O. A we have found, and then we have radial component, CA, and the tangential component of CA. Of these 4 lines, we know 2 of them. We know the radial components of C and the radial component of C relative to A. This was done from your velocity diagram, and I have my list of calculations ready. We're going to draw in the 2 radial components, which we know. We can then draw in the tangential acceleration lines, and where they cross, that's going to be point C. So radial C relative to O, I have my ruler along the link. Now C relative to O means C is rotating about point O, and my radial acceleration always points towards the center of rotation. So my radial component will be down. Ruler on the link, set square on the ruler, and let's draw. Oops. This way. Just make sure it's got some dashes so it's easy to see. And the length is 5 centimeters. So here we go. And radial CO. Now I'm drawing in the radial line of C relative to A, ruler along the link CA. This means C is rotating about point A. Towards the center of rotation, my line goes to the left. So set square and parallel line. Now this line is only very small. It's going to be about 0.5 centimeter. I'm still going to label it radial CA. So there are my two radial lines. Now I'm going to draw in my tangential lines, remembering that they are perpendicular to the radial acceleration or perpendicular to the link. I don't know the length or the direction, I just know the location. So this line could extend down there. And then we have this line, the tangential component of CA, perpendicular to the link CA or the radial acceleration. And where these two cross, this is point C. So before I move on, clean up my diagram, I'm going to draw in my tangential lines, and this will be tangential CA, and I need to draw in the total acceleration. So this would be acceleration of CO. I can get from my fixed point to C by adding the radial plus tangential, or I can follow the direction of the total acceleration. And we'll do the same with C relative to A. So radial, tangential, close the triangle with my total acceleration. Okay. Next we're finding point B, because C, B and A are all on the same link. As we have done before, we're going to use a ratio. If they're on the same link, they have the same angular acceleration. So acceleration CA on acceleration of BA equals radius of CA on the radius of BA. Acceleration of BA is our unknown, put that on the left hand side, equals acceleration of CA by the radius of BA on the radius of CA. We know the length of the total acceleration, C relative to A. Remember, this is total acceleration we are using in our ratio. So I have that as, let's see, 12.7 centimeters. And then multiplying it by the ratio of the links. Those values are given in the question in millimeters. Because this is a ratio, the units cancel, so I don't need to convert them yet. So we have 500 on 700. And if you do this calculation, I get 9.07 centimeters. That is my acceleration of BA. B relative to point A. So when I measure on my diagram relative to A, so I start from point A, I measure down 9.1 centimeters. This is point B. Before we move on, total acceleration. So acceleration b relative to your fixed point. And now we can look for the next point in the diagram. Back to my mechanism. I have C, B and A all completed. Point B is connected to point D. So that's my next point I'm going to find in the diagram. A new point means a new equation. So acceleration of D equals acceleration of B plus acceleration of D relative to B. I know point B. D is my unknown, which is why it's on the left-hand side of the equation. D is connected to a fixed point. So we have the radial D relative to O and the tangential D relative to O. And then D relative to B has radial and tangential components. So you can see here that the method is the same. We write out an equation, identify the components, we know the two radial components, I'm going to draw those in, and then I will add the tangential lines. Where the tangential lines cross is going to be point D. So first of all, I'm going to draw in D relative to the fixed point. So D relative to O means my radial acceleration points towards point O. Put the ruler along the link, set square along the ruler, first one, second one, and this value is very small. So I'm going to give it an arrow and then radial DO. My other point is D relative to B. D relative to B means B is my center of rotation and my arrow points upwards. So from point B, I have my ruler along the link, set square on the ruler, second set square, and this value is going to be 6.8. So I have my line, let's measure 6.8. And this is radial dB. From these two components, I'm going to draw in the tangential line, and where they cross is going to be point D. And this line, quite tricky to see because it's so small, but we do our best. So here is point D. I'm going to label my lines with arrows, clean up the diagram, draw in my total acceleration, so acceleration dB, and my total acceleration of D. So now we're ready to find the last point, point E. And you can see from the mechanism that E, O, and D are an L-shaped link. So if this is my L-shaped link, this is D, this is E, and they move together. From our diagram, we can see that point D is pointing upwards now. This is the total acceleration of D. So on my L link, if D points up, then E is going to be at 90 degrees to the other side. So let's draw in the direction. To get the length of the line, we can use another ratio because if they're on the same link, they have the same angular acceleration. So acceleration of E on acceleration of D equals the radius of E relative to the fixed point on the radius of D relative to the fixed point. Acceleration of E equals acceleration of D on radius of E on radius of D. The acceleration of D, we know, because I can measure this line. So this is about 5.8. And our ratio will be 400 on 200. So if I multiply this by 2, I have 11.6 centimeters for the acceleration. I'm going to measure this as accurately as I can. Here is E, acceleration of E, and that is my completed diagram. So here again is my finished diagram. I've actually moved the location of some of the labels and arrows to make it clearer, because as the diagram progresses, it can get quite confusing. So I hope you do the same when you're submitting your diagrams. I also have all my calculations, so my radial acceleration calculations, I have my relative equations, my ratios, another relative equation, and the ratio for point E. So please show everything in your diagram. The question asks for the acceleration of point E. So for the final value, you can measure the length of this line, remove the scale, and present your solution in terms of meters per second squared. I hope this was helpful. If there is still some confusion, please go back and watch the workshop video, as well as have a look at the workshop slides. As you do more of these, the method becomes more familiar and you're doing the same process over and over again.